I will now tell you about a fundamental principle in quantum mechanics known as quantum superposition. This principle says that any two or more quantum states of the same physical system can be combined, or superposed, to produce another valid quantum state of that system. The quantum superposition principle is a powerful tool for understanding the behavior of quantum systems, and lies at the heart of several fascinating quantum phenomena that we will explore later in this course. Let's see how this principle works. Suppose psi sub 1 represents a possible state of a quantum particle. The wave function psi sub 1 is a function of position x and time t, and it satisfies the Schrödinger equation. As before, h hat represents the Hamiltonian, which is the total energy operator of the system. Furthermore, suppose that a wave function psi sub 2 represents another possible state of the particle. Similar to the first wave function, psi sub 2 is also a valid solution of the same Schrödinger equation. The superposition principle states that by multiplying the wave functions psi sub 1 and psi sub 2 by arbitrary complex numbers, c sub 1 and c sub 2, and adding them together, the resulting function psi remains a valid solution of the Schrödinger equation. Thus, psi represents a new possible quantum state of the system. Naturally, the coefficients c sub 1 and c sub 2 must be chosen such that the wave function psi is properly normalized. Psi is referred to as a superposition state. Loosely speaking, when a quantum system is in state psi, it exists simultaneously in two different states, psi sub 1 and psi sub 2, which may have very different and seemingly incompatible physical properties. We will soon explore a concrete example of such a superposition state. But first, let's confirm that psi indeed satisfies the Schrödinger equation. Let's start with the left-hand side of the Schrödinger equation, where we have IH bar multiplied by the time derivative of psi, and show that it equals the right-hand side, h hat applied to psi. First, we'll express psi in terms of psi sub 1 and psi sub 2, and expand the brackets. Then, using the fact that both psi sub 1 and psi sub 2 satisfy the Schrödinger equation, we can rewrite our expression as h hat acting on the superposition state psi. This calculation demonstrates that the superposition wave function psi indeed satisfies the Schrödinger equation, thereby representing a legitimate state of the system. To illustrate the superposition principle in action, let's consider an example where we construct a superposition state from two distinct coherent states of a harmonic oscillator. Let's use psi with subscript cs to denote the coherent state of an oscillating particle, initially released from position x sub 0. Thus, the function psi sub cs depends on position x and time t, and is parametrized by the particle's initial position x sub 0. As we have previously established, this wave function can be expressed as a normalization constant, multiplied by an exponential function. The argument of the exponential function consists of a real part, which specifies its Gaussian envelope, and an imaginary part, that represents the phase of the wave function. In this expression, alpha stands for the product of the particle's mass m and the oscillator frequency omega, divided by twice h bar. Now, let's consider a state psi, that is a superposition of two distinct coherent states. The first coherent state represents the particle initially released from the point x sub 0, while the second coherent state corresponds to the particle starting from the point minus x sub 0. The two coherent states enter the superposition with the same weight, denoted as c, which plays the role of the normalization constant. Finding the exact value of c is left as an exercise, with a detailed solution provided. In particular, working through this exercise, you will discover that the normalization constant takes on a simple, parameter-independent value when the two coherent states are initially separated by a distance much larger than their width. More precisely, if the absolute value of x sub 0 is much greater than 1 over 2 square roots of alpha, which represents the spatial width of the coherent states, then c simply equals 1 over the square root of 2. To visualize the superposition state and its motion, let's select specific values for the parameters. We will use atomic units, where h bar and the particle's mass are both set to unity. We will also take the oscillation period as the unit of time, making omega equal to 2 pi. Finally, let's set x sub 0 to be 1.2. With these parameters, the initial probability density of the superposition state, namely, the squared modulus of psi, features two separate peaks, as illustrated in the upper panel of the figure. Here, the horizontal axis represents x, and the vertical axis depicts the squared modulus of psi. The lower panel of the figure depicts the parabolic potential governing the motion of the oscillating particle. One can regard a particle in the superposition state psi as existing simultaneously on both the left and right sides of the equilibrium point, meaning that the particle possesses two classically incompatible properties. Superposition states like the one here are often referred to as cat states. This term originates from the famous thought experiment by Erwin Schrödinger, highlighting the counterintuitive nature of superposition states. In his thought experiment, Schrödinger explored a scenario where a cat could be in a state where it is simultaneously dead and alive. The figure shown here illustrates the superposition state psi at the initial time t equal to 0. Now, let's allow time to progress and observe how the probability density of the state evolves. We observe that, as the two coherent states approach each other, they begin to interfere, forming a structure with multiple peaks. Subsequently, they separate, and the individual Gaussian packets re-emerge. These oscillations continue indefinitely,